So I'll read off here because my board is not the greatest. In general, a circle of radius r centered at the origin follows this equation: x squared plus y squared equals r squared. That's every circle centered about the origin, 0, 0. The unit circle has a radius of 1. It always has a radius of 1. That does not change ever. So we can therefore say that x squared plus y squared equals 1. So if ever you hear or are asked, is this on the unit circle? Is this coordinate on the unit circle? Remember how I told you if it's a factor, you instantly write remainder is 0? Yeah? And I've told you other things that if you hear it, you must do this. You say x-intercept, make y equals 0. Y-intercept should be x equals 0. If it says on the unit circle, they're asking, does it fulfill this equation? X squared plus y squared equals 1. Because if the radius is 1, it would be x squared plus y squared equals 1 squared, which is just 1, right? So if a coordinate actually fits on the unit circle, then it should fulfill this equation, okay? So if ever you're asked that, a point on the diploma, which they have done this before, not last diploma, but the diploma before, they asked questions just like this. Is this on the unit circle? Well, it's easy if you know this equation. Plug the x in, plug the y in, and when you square them and add them, does it equal 1? Yeah, it's on the unit circle. Does it not equal 1? Then it's not on the unit circle. That easy. All points p, x, y on the unit circle satisfy this equation. Every single one. Now, what's deceiving about... that's not good. Okay, what's deceiving about the unit circle on the back wall? I'm going to help me move this thing over so it's not completely covering the unit circle. Oh, what's going on? I don't know. Being recorded too. Anyone who's not in this class that watches these videos is probably crying or like, what is this lady doing? Just wrecking stuff. Whoa. I think you put it too far.
Too far.
There. Teamwork. There we go. And boof, to fall down. That's okay. All right. Still recording. Good times. All right. So if you look at that unit circle, the big deception of the unit circle is people think that those are the only points on the unit circle. That circle is connected by a whole bunch of little infinite points, right? If you take all those little teeny tiny points and you connect them, it makes the whole circle, correct? People are like, no, those are just lines. Well, actually, they're little coordinates that are attached to each other that makes that exterior line around the unit circle, right? So there's an infinite number of points around that unit circle. Those are just the special ones that we look at. But I can give you any point that falls on that unit circle and ask you if it's on. So some people will be like, it's not on the unit circle. It's not on the one that we draw. It's not a point that's on there, but it's still on the unit circle. That doesn't mean just because it's not one of those points doesn't mean it's not on the unit circle. So don't fall to that. Some people do. So these are your special triangles that you were given, and based on our special triangles is how we develop our unit circle. So the 45-45 triangle has our side lengths of 1 and our hypotenuse of root 2. In front of you, you can actually see that. This one here, our 60-30-90 triangle, is a 1, 2, and a root 3. Okay? So when we go to set up our unit circle, which I'm going to hand out to you. Where did I put it here? When we go to set up our unit circle, it's basically a whole bunch of 30, 60, 90, and 45, 45, 90 triangles. For a lot of you, this will be a review. For a few of you, you'll have not seen this. No. Okay. So we're just going to look at this quadrant first. If you've seen the unit circle, that's fine. You still haven't seen the radian measure, and we're going to go through it anyways. So you don't have to draw this. Please just pay attention. You don't need to draw this on here. Awesome. Okay, you guys, shh. Right here's a 90-degree triangle. Okay, it's a 90-degree triangle. And our first angle down here is 30 degrees. Because we're going to break our way up to 30, then 45, then 60s. Everything on this unit circle is all broken up to 35, 45, 60, and 90-degree reference angles. Reference angles is the angle from the x-axis up, right? Or down. So this would be a 30, 60, 90 triangle. This would be a 30. This would be a 60. That's a 90. And I'm going to show you how you actually come up with the unit circle. After that, most people just go with sheer memorizing in orders. That's fine. But I want you to know why. So if you look at the 30, 60, 90 triangle that's in front of you, between the 60 and the 90, you have 1. Between the 60 and the 30, you have a 2. And between the 30 and the 90, you have a root 3. What's very important about the unit circle is that the unit circle coordinates are always cosine. Cos theta makes up the x coordinate. Sine theta makes up the y coordinate. Cos theta makes up the x. Sine theta makes up the y. So if ever you're asked cos of 30, you could just go to 30 degree and pick the x, right? Because that would be cos of 30. Reminding yourself of all the stuff you did last year. This is all from last year. Cos 30, sine 30. So this first one is cos 30. Cos is adjacent over hypotenuse, or adjacent is x, hypotenuse is r. Remember we did x's and r's and y's and r's last year? So it's going to be x over r. X is root 3, r is 2. Now people still like adjacent and hypotenuse. We're looking at 30. Adjacent to hypotenuse would be root 3 over 2. But on a unit circle, x's and r's and y's make more sense because this is an x value, this is a radius value, right? Now some people will say, well, that radius is 2. That's not 1. You told me the unit circle radius was 1. If we look at the unit circle before it's actually rationalized like this, it makes this be a 1, and then these are actually fractions. So then you have a fraction over a fraction, and it makes it harder to make the unit circle. So I just use the 30, 60, 90 triangles not in fraction form just because it's easier to fill in. So you get adjacent over hypotenuse. So it's going to be root 3 over 2, or x over r, root 3 over 2. And then our y is always our sine, right? So it's going to be our y over our radius, or our opposite over our hypotenuse. So we get a half. That's how we get root 3 over 2 and a half. Now, this little triangle is a perfect reflection of the little triangle over here, is it not? It's the exact same thing, isn't it? So you can get the same point. Root 3 over 2 and a half. But what's my catch? When I'm in this quadrant, what happens? Because this is 0, 0 here. And this is the x-axis. And this is the y-axis. Points in my quadrant number 2, what are they? Yeah. X is negative, y is positive. Yeah, always. So we get the exact same coordinate, but because it's found in quadrant 2, our x's are negative. Now down here, I'm going to get that exact same coordinate. Root 3, 2, half. These are fractions, right? Quadrant 3, what's with our x's and our y's in quadrant 3? Any point down here, what's it going to be? Negative, negative, right? Like if I say, oh, what's this point down here? Oh, negative, I don't know, negative 0.5 and negative 0.5, let's say. They're going to be negative, anything in quadrant 3. So both of these are going to be negative. And what happens over here? We get the same thing, root 3 over 2 and a half. But what are my signs in quadrant 4? My x's are, this is a positive x to get me here, right? and a negative y to get down here, correct? So to get over here is a positive x, to get down here is a negative y. This is literally a coordinate. This coordinate's at root 3 over 2.5. Okay? So we have a negative y. So that's something you can write here too. So look, this is positive y, negative x, positive x and y. This is negative x and y. And this is positive x, negative y. Those should just be something you understand though, right? When it's in that quadrant, what are all your points, right? Your points in this quadrant are all negative x's and positive y's. In this quadrant are all negative x's and negative y's to get down here. To get over here, positive x, negative y. To get here, positive x, positive y. So that's the 30, 60, 90. I'm going to skip the 45 in the middle here just to prove a point. This is also a 30, 60, 90. The only catch is it's the opposite direction. This is 60 degrees to get me to this line, right? This is 60. If this is 60 and this is 90, this still has to be 30 because all triangles add up to 180 degrees, right? Still a 30, 60, 90 triangle. Our numbers just moved. So between 60 and 90 is a 1. Between 90 and 30 is root 3. And our hypotenuse is 2. Same deal. This is cos this time. Cos is x over r. Okay, so it's going to be 1 over 2. And then this is going to be y over r. So root 3 over 2. So they're just the same but flipped, right? Because it's the exact same triangle, just flipped. So the same thing goes here. A half and root 3 over 2. Except my x's are all negative here, right? Then I go down to this one. It's going to be a half and root 3 over 2, but they're both negative. And this is going to be a half and root 3 over 2, but my y is negative. So it seems really complex, but it's literally just the same thing stamped in all 4 different quarters. And then your middle one is a 45, 45, 90. So here's your 90. Here's 45 degrees. And this has to be 45 degrees because the triangle has to add up to 180. This is 1, 1, and root 2. And like I said, this is in the form so you don't have fractions. I've already gotten rid of the fractions. So this is cos. Cos is x over r. So it's 1 over root 2. And then this would be 1 over root 2. I never write them like that. I write like that to prove a point. We always rationalize our denominator, which means we don't have radicals in our denominator. So if I went down here and I rationalized 1 over root 2, how do you rationalize? How do you get rid of a radical in the denominator? Multiply by that same radical, right? If there was like this plus another radical, then you'd have to multiply by their conjugate, the two with opposite signs. But that's not what we're doing here. So multiply by root 2 and root 2. So we actually get 1 times root 2, which is just root 2. And what's root 2 times root 2? 2. Root 2 times root 2 is root 4, which is 2. That's why you multiply. Whenever you multiply two radicals together that are the exact same, you get just that number. Because you're going to get root 2 times root 2. You multiply the numbers underneath the radical signs together, which is actually root 4. And root 4 is 2. So that's the form I always put on my unit circle, root 2 over 2. What do you notice about all their denominators? They're all over 2. This one's going to be negative. This our x's are negative. Root 2 over 2, root 2 over 2, they're both negative. Root 2 over 2, root 2 over 2, that one's negative. Are negative, positive. So positive, positive in quadrant 1, negative, positive in quadrant 2, negative, negative in quadrant 3, and positive, negative in quadrant 4. So for the most part, for most of you, this is just, we've done this before. Now, if you go on the arms, those are the easiest coordinates to do. What's the radius of your unit circle always? 1. Now, like I said, when I did those special triangles, I popped them out of fraction form, so that's why they didn't look like a 1, right? But this is 1, a distance of 1. This is a distance of 1. This is a distance of 1. This is a distance of 1, right? Radius all the way around is 1. All of these are 1s all the way around. So if I went to this point here, what would my coordinate be to get me to that exact point? How much should I go over? 1. You know how many people want to say like 20 because it looks like it's a really large distance? So like, 5, 10, 9. It's 1. It's always going to be 1. So I went over 1, and how many did I go up? This is my x-axis, right? How many did I go up? 0. So this is 1, 0. Went over 1, up none. This one, this is my y-axis right here. So I went my y, this is my x. So here I went over none, up 1. So 0, 1. How many did I go over to get to here? 1, but what is it actually for this coordinate? Negative 1, 0. This coordinate would be negative 1x, right? And up none. And then this coordinate to get me down here on the y-axis, this would be at 0 and negative 1. I'm hoping for most of you this is just review. So now we have to label our degrees, which is what we did last year. But this year we also have radians, but it's not hard to change a degree to a radian. So I just do all my degrees first. So this can be 0 degrees, or 360 degrees, technically, right? That's why there's the 2 lines there. Then all of the special triangles use reference angles of 30, 45, 60, or 90, right? I can go this way, 30, 45, 60, or 90. I showed you with all the triangles, right? 30, 45, 60, 90. And then 30, 45, 60, 90, right? That's all I'm doing. So I label my big ones first. So this can be 0. This would be 30 degrees. This is 45 degrees. This is 60 degrees. And this is 90 degrees. Now I'm going to label all my arms because it just makes it easier. So that's 90. This is how many degrees to get me here? It's a straight line, 180. And then how many to get me down here? 180 plus 90, right? So 270. Now, once I have those arms, it's easy to figure out the other degrees because I have reference angles of 30, 60, 30, 45, and 60. So if I go 180 minus 30, what do I get? 150. Because this is 30-degree reference angle, right? And this is a 45-degree reference angle. So what's 180 minus 45? 135. And then I go 180 minus 60 because this is a 60-degree reference angle, so it's 120. Then I can work my way this way. 80 plus 30, because it's still a 30-degree reference angle. 80 plus 30 is 210. 180 plus 45, 225. 180 plus 60, 240. Oops, that's a 40. Then I can work my way this way. 360 minus 30, because I have to subtract it, 330. 360 minus 45, 315. 360 minus 60, 300. How can I convert these quickly to radians? Degrees to radians, pi on top, technically, right? So you're multiplying by pi and dividing by 180. So what you can do is just go 30 divided by 180. See if you look here on your notes, it shows you too that they can be scaled down to fit. So you can take these special triangles that are given to you and you can scale them down, divide by root 2 to get this to be a 1 instead, and then these would be 1 over root 2, 1 over root 2. And then you'd actually have to take those values and divide them out to be dividing a fraction by a fraction. So instead of making them b to radius 1, I just use them how they were for less work. Okay, I'm going to get you guys to flip ahead a few pages till you get to this. It's not example 1 for you. I rearranged them better after, but I had photocopied them for you guys already. So flip to here. These coordinates are really, really, really easy to do once you actually have the unit circle. Without the unit circle, they're very hard. You'd have to go to your special triangles. You'd have to find out what reference angle these guys get, and then figure out where they fall in cast rule, and then give the sign properly that way. You're going to flip ahead a bit till you see some that look like this. But once you have your unit circle done, the coordinates are very easy. You just pull them off the unit circle. However, if your unit circle is done wrong, you're going to get all your questions wrong. So that's why it's so important that you can get to the unit circle. So you're flipping ahead a few till you get to an example that looks like this. They're called example something else in yours. Your example 8 and 9, I think. The top one's example 4. So go to example 4 first, and then 8 and 9. So state the coordinates of the intersection of the terminal arm and the unit circle for the following rotation angles. Basically, it's example 4 for you. Go to pi over 2. This p means the point at pi over 2. So go to pi over 2, which is 90 degrees. What's your point there? 0, 1. At 90 degrees, the coordinate's 0, 1, right? Very easy to answer off of your unit circle. Now, negative 3 pi. This one doesn't fall directly on the unit circle, but if you find the coterminal angle that works with it, the coterminal angle follows on the unit circle. So it'll always fall on the unit circle somehow, but sometimes you have to find the coterminal angle to it in order to find it to fall on the unit circle. So negative 3 pi isn't on the unit circle. The unit circle only goes up to 2 pi, right? And negative 2 pi, you could still work to be on the unit circle. But I always work it till I get my first positive angle. So I'm going to go negative 3 pi, and I'm going to add 2 pi to it. What do I have then? Because 2 pi is adding was what you do in order to get a coterminal angle, right? With a radian measure. You're going to get negative pi. Still not positive, so I add another 2 pi to it. And then I'm going to get positive pi. So that's the angle that I'm going to look for on the unit circle. Now, I'm just going to use this one up here just to show you. Negative 3 pi, you go counterclockwise and you start here. It's going to be, this would get me to negative 2 pi, right? Get me back to here. And then I'd have to go another half to get me to negative 3 pi. What is that on the unit circle? It's in the same spot as pi, correct? That's all you have to do. So you can either find the positive coterminal angle that works with it on the unit circle, or you can draw it till you get to that arm and just write what it is as well. Either way works, okay? So I could literally find 3 pi by going, okay, that's 2 pi, that gets me to 3 pi, and then just state my coordinate, which is negative 1 and 0. Or if you don't like doing that, find the first positive, the principal angle, between 0 and 360, which is pi, and go to there and state it. It's the same thing. Okay, either way, whichever way you like best do. 7 pi over 2, is that on the unit circle? No, and if radian measure scares you, change it to a degree if you want. Degrees to radians, pi on top. Radians to degrees, pi on bottom. So you're going to times by 180 over pi. Your pi's cancel. What's 7 times 180 divided by 2? 7 times 180 divided by 2. I'm going to ask someone. And that someone is going to be Mackenzie. What did you get? 630? Okay, 630. You can either draw it and find out where it lands, or what could you do? You could find the coterminal angle back. How can I work my way back? 630 minus 360 gets me what? What's 630 minus 360? Nolan. 630 minus 360. 270. Is that on the unit circle? Yes. So the coterminal angle to this should be 270. Bless you. Because it was 630. At 270, my coordinate is at 0 and -1. Just go onto your unit circle and pull the coordinate off. $720. If I want to, yeah. 720, if I want to draw it on the unit circle, is rotation twice. So it's going to be like this. That's 360. And another full rotation is 720. So it gets me here, which is 10. Or I could find the coterminal angle. 720 degrees minus 360 is 360. Because remember, the coterminal angle terminates on the exact same arm. That's why it's coterminal, right? So if it terminates on the same arm, it's going to have the same coordinate. Does that make sense? So there's numerous ways you can do this. You can find the coterminal principal angle, first positive, on the unit circle, pull the point off. You could physically draw the angle and find out which arm it terminates on the unit circle. Put the point off, right? If it's a radian measure, you could change it to degrees and do the same thing. So it's up to you. There's no right exact way to do it. It's whichever way you think is easier. Okay, now you're going to go to 8. Example 8. I know it says 2, but for you it's example 8. Using the above information, determine the coordinates. It should be below. Bad wording. Determine the coordinates on the unit circle of each. So exact same question as this one, except you're doing it. Go. $60 degrees is right off the unit circle. 60 degrees is in your first quadrant. It's going to be 1/2 and √3/2. What's great about pi/6 is that's a pi/6 reference angle. So you know at the very least, it's going to be √3/2.5. Even if you don't know the sign, it's going to be that. So that should at least be able to narrow down some of your multiple choice questions if that. Because if it's pi/6, it's a 30-degree reference angle. If it's pi/6, it's a 30-degree reference angle. So it's going to follow those points, right? We do have to figure out where the heck it is, though, in order to get the correct sign. And 7 pi/6 is right off your unit circle. It's in quadrant 3, so they're both negative. 240 is also right off the unit circle. 240 is 60-degree reference angle at -1/2 and -√3/2. 120 is a 60-degree reference angle right off the unit circle. So it's going to be -1/2 and √3/2. And 5 pi/3. Now what some people do is they'll go find 5 pi/3, the 300, and they'll say, okay, so it's 1/2 and -√3/2. Negative 300 degrees or negative 5 pi/3 is not the same as positive 5 pi/3, right? It would technically be like, if this would be negative 300 degrees. Okay? Negative 300 degrees You'd go past 270. This is 270, negative 270, and another 30 degrees. So it would actually get you here, right? Which is the same place as 60. So it would be a half and root 3 over 2. What you can do is you can find the reference angle or the positive principal angle to it. So coterminal, you could add 360 and you'd find out that the coterminal angle is 60 degrees and do it that way. 19 pi over 6. Well, you know it's a 30-degree reference angle, so it's going to be root 3 over 2 and a half at the very least. So that should be able to narrow it down if you're stuck on a multiple choice at the very least. 19 times 180 divided by 6 is 570 degrees. I like finding coterminal angles myself, so I minus 360 from it, and I'm going to get 210. And then I go to 210, and it's negative root 3 over 2 and negative a half. And then negative 3 pi we did already. Negative 3 pi ends up back at pi, so it's going to be at negative 0, negative 1, and 0. Okay, now you're going to flip back to the second page. I know it's way out of order, but you're going to flip to the back side. And come back to that one. This one. So you're at point A, blah, blah, blah. The very, back of the first page we started on. It just says examples. It doesn't actually say, and it just literally says examples. So determine the missing y coordinate for each point on the unit circle. It says on the unit circle. If it says that, it has to fulfill this. If it says that, it has to fulfill this. If you forget x squared plus y squared equals y when it says on the unit circle, you're going to sit here for a very long time and have no clue how to solve for y. So we have an x. We need a y. Plug it in. Get the y. So you can get negative 4 over 5 squared plus y squared equals 1. Negative 4 over 5 squared is 16 over 25. Plus y squared equals 1. Then you subtract your 16 over 25 over, and you get y squared equals, now 1 is just 25 over 25, and you have to do that to have a common denominator. So y squared equals 9 over 25. Now this is the catch. When you take the square root of anything, you have to take the plus or minus. Remember we went over this already? When we did inverses with quadratics? So it's going to be y is going to be plus or minus, equal to, sorry, plus or minus 3 over 5. Because the square root of 9 is 3 and the square root of 25 is 5. So you can break them both down into 3 and 5. Now that's not the answer. Positive or negative is the answer. That's why they tell us this. It's in quadrant 2. Is y positive or negative in quadrant 2? Quadrant 2 is here. Positive. So my answer to this is 3 over 5. You try point B. That's a 9. I really wanted it to be 81 because it would have been nicer, but it's not. Now, some people say it stays like that because I can't square root of 91. Do you remember in grade 10? I know this is going way back when, but in grade 10, if we gave you root 2 over 25, we taught you guys that you could break the root up over both. So you could write this as root 2 over root 25, which would be root 2 over 5. You can do that with radicals. You can split the radical up over both separately. Or if they're separate, you can split them over top together, right? So, and that was the start of teaching you guys how to rationalize the denominator in grade 10. So, we actually get y equals positive or negative root 91 over 10. It's in quadrant 4. That means it's down here. Y is negative. So it's negative root 91 over 10. We're going to skip to the next one and go down to the bottom of your page. Is each point on the unit circle? I've seen this before where they ask, like, is the point on the unit circle? The only way you have to worry about it is if it says on the unit circle, x squared plus y squared equals 1. If this is true, it's true. So the equation of the unit circle is x squared plus y squared equals 1. The right side of this is 1. Right side of the equation. The left side is going to be 0.65 squared plus negative 0.76 squared. What does it get you? Some people say, yeah, that's true. But if I gave you this, totally ignored the question completely, and I just threw an answer to you and I said on a test, tell me what's true or false. Is 1.001 equal to 1? What would you tell me? No. But in this example, you're like, yeah, it's 1. If I gave it to you on a piece of paper, without the previous knowledge, you'd say, no, this is not true. It's not true. 1.0001 is not 1. I know if you round it, you might feel it is. It's not. So, not on the unit circle. Because this is not true. This one we know is on the unit circle. It's in quadrant 3. It's 225, right? But let's prove it anyways. Negative root 2 over 2 squared plus negative root 2 over 2 squared equals 1. Square negative, it goes away. Square root, it goes away. So you're going to get 2, square root squared is 2, and then 2 squared is 4, plus square root of 2 squared is 2, plus 2 squared is 4. What you do when you have common denominators, you keep the denominator and add the tops. 2 plus 2 is 4. Don't do number 1. Do 2 to 5, C and E. That reduces it drastically if you didn't know. Six. 9AB. 10. 13. Same page. So it's cut down drastically. It needs to be done. I will be coming around and checking page 175 right now from the homework from the weekend.